I am back from my vacation, so I will start catching up on Advent of Code 2004, starting with day 16. So I've already pre-read the description, so I have some small idea on how I will approach it, but let me explain what the problem is. So we're getting an input of a maze where reindeers are going to race from start to end, and the goal is for them to have the lowest possible score when running through the maze. And the movement is either one tile at a time, and also rotating clockwise or counterclockwise, and the rotation is very costly because it takes a lot of time, so increases their score by 1000 points. So it is always better to just run in one direction instead of rotating. So that's the idea, and our goal is to find the lowest possible number of lowest cost path through the maze, basically. So that's what we are working with, and the important thing here is that initially we're starting facing east, so to the right. So that's the idea of the problem, and my idea of how I will try to approach it would be to use Dijkstra algorithm, basically, to walk through the maze and try to find the lowest possible. So let's start solving this. So I will take the example input and put it here as a test data. And now let's see what we can do with it. So first, I will, of course, as usual, read the input. So private int width, private int height. And as usual, because this is happening all the time, I think it would be useful to create some helpful method for it, so some generalized method to read in a map of characters, but let's keep it for next time. But yeah, it would be probably a good idea because it's happening very frequently in these problems. So let me see. So this is the input, so I will first need to read in lines, which will be await put reader read all lines, and then we will do width equals lines 0, height number of lines. We initialize it and we do exactly this. So we read in the line and we read in the map. So that's reading the input itself. This is going to be count. And okay, so can we actually do read input async? So that is more clean this way. We hide it in there. So then what we want to do is to do kind of a Dijkstra algorithm. I think it's priority queue is the yes. So priority queue is the collection that allows us to simulate a heap, a kind of min heap data structure. And in case of .NET 9, they added a very useful new method, which is queue decrease update priority. So let me see what's the capacity. No. In queue, the queue. It's associated. I mean, okay, not this one, but there was a new way to set priority. So how was it called? Is this actually .NET 9? Yes, it's targeted .NET 9. So what is the update priority? Let's see. Priority queue update priority C#. So there's a new method somehow that allows this updating of priority. Queue. Okay, not here. Interesting. I thought it was priority queue, but maybe I missed it. So 9 priority. Okay. This one. Remove priority. Okay, priority queue. New remove method, yes. Huh. Well, essentially, it seems like you just remove an add or something like that. So we'll see what happens. So let's first do some data structure that will hold the state that we are in. So record state, and it will be point position, point direction, and also int cost. And that will be our kind of state that we will be adding into the queue. And initially, so find lowest cost. Lowest cost. Find lowest cost, and this will give. So search for the lowest cost. So it will be find lowest cost method, and that we will output there. So just lowest cost to string. So now we need to find the implementation for this. So states priority queue state, or rather, actually we can keep the cost directly in there, I guess, or we can well, at least we can do it like this and duplicate it, stay there. So can do visit it. Oh, actually we can also store private point start, private point end. So this will be the start and end point. So when we read in the map, if line, so map xy equals s, we read it. So it's the start and end will be end, and we also can do just x equals dot, so that we don't have to check for s and e separately. We know that's that point that we want to find. So that's done. Now enqueue the start, and that's going to be the direction of 1 0 because we're looking to the right, and cost of 0. And so this is a state that we are adding. Now while states count greater than 0, we will get state is a queue, and we will have finalized. So we'll have some kind of minimum costs array, so the dictionary. So that will be a point, or rather, let's do it like this. That's good. So state and int. So there will be the minimum costs for given states. So minimum cost will be the state, the queue, but we will need also the priority. Okay, so when we dequeue it, finalized. So this is the hash set. So this will store our costs, the current minimum costs that we have for each state. So for this starting state, it should be this one. So starting state we'll have this. For starting state, we have priority of 0. We'll add with the 0 as a minimum cost. And when we dequeue, then we add the state to finalize. So finalize add state. There's nothing small that can improve it, so we add it as finalized. Now for if the state is actually if state position, well, actually we can reach the end with 4 different directions, so it's not something we want to finalize immediately. At the end, we will return for each direction in directions without diagonals. We will return the best end state. And it's going to be max value, and we will do best end state equals minimum of the minimum costs for yes, so basically we get the end state with the direction and its max value as default if the value is not there. So we find the best state and that's what we return. Okay, so we have this, and for each direction in directions without the diagonals, we will see what happens. So the options that we have in a position that we are is either going forward, that's one option, so we go forward, or we rotate clockwise and we rotate counterclockwise. So if we go forwards, so next will be state position per direction. So if the next, if finalized contains next state will be this. So if it contains this state already, if it doesn't contain the state already, and we improve, so minimum costs. No, so if the minimum cost is not there yet, so minimum cost try get value for next state out value cost next cost. So if we don't improve, if it's already there, and or rather, if it's not already there, or we improve it, so next cost is greater than next, so state, minimum costs state plus 1, then we will improve it. So we add set next state minimum cost state. We have to enqueue it with the new cost that we set, and also remove the previous one. So states remove next state. So we remove it. So we remove the original one there. So that should be it. So we remove the previous one if it's already there, and we just enqueue a new state with the new value. So that should be this, and we basically do the same thing for clockwise and counterclockwise. So So we can do next if better, improved. So state, next state, in cost, and we basically just take this logic into a separate method there. We can actually move it. Let's move it here. That's fine. So we keep it in line. So if the next state is there and the next cost, the cost that we have is better, then we improve it like that, and we said that's fine. Okay, so we add next improved, add the new one, then we do the rotation. So next state equals, so the rotation clockwise is, let's verify if this is correct. So if you're looking to the right, we want to clockwise look to the down. So if this is +1, then it's going to be, if x is +1, then it should be 0 + 0, 1 to look downwards, and counterclockwise will be minus. So if it's going to be, so if we're looking downwards, so it's going to be -1, right? So if you're looking, if we were to look upwards, it would be -1, 0, -1, and we want to have -1, 0 if we're rotating counterclockwise. Whereas, so -1, 0, so this one, and we want to have this for clockwise. So we're looking, if it's -1, 0, -1, we want to have 0, 1, 0, right? Yeah, that seems okay now, I think. So now we just add next if improved, and the cost there will be +1000, +1000 here. Okay. And this is gonna process everything. So hopefully when this finalizes, we should be done completely with the whole maze that's there. So let's verify what happens if I run this. This data is there, right? Yeah. Okay. So day 16. So we're getting stuck somewhere. Question is, why is that? So it keeps adding new things, but what I'm not checking, so not finalized, it contains next stage. So we are, oh, I think I'm doing something wrong here. I'm not that's okay. That's wrong completely, because I'm not checking for the boundaries at all. I'm not checking for the map contents at all, so that's definitely wrong. I'm just doing some random magic there to go everywhere as if it was an empty space. So that's not what we want. So we need to make sure that if next state position x less than 0, or like if it's out of bounds, then we just return. And if next state is a wall, which is actually this character, yes, then we also return. So we don't add the state there if it's actually something nonsensical. That is definitely important improvement. So let's see what happens now. Hopefully better. So 7036. 7036. Okay. And second example, let's see. We can try the second test example as well, just to make sure that we are not missing something here. 11,048. which is correct. Okay, let's try the big one. Save it and let's run it. Put file. Here we go. So this number, which is correct. Okay, so we have the first part of the problem solved. So now let's continue with part 2. So in part 2, our goal is to figure out whether specific tiles are on one of the best paths through the maze. So we're trying to find which tiles are part of any best path through the maze. So if there are multiple, then we need to find all of them that are actually the best. So what we will do is when we walk through the maze, we have to make sure that if we are checking, if we're not actually improving the cost, but it will be the same cost, we know that there was another way to achieve the same cost for the same state, basically. And as long as we track it, we should be able to backtrack to where we came from. Right, so let me check. I will take the input, put it here. And now we have to track where we came from as well. So source states. And it's going to be a dictionary of state with a list of state. So this will be the states where we came from while arriving at the current minimum cost of a given state. Find best path tiles, tile count. So this will be a new method name. How many tiles are part of the best, at least one of the best paths? Yeah. So source states will be the states how we arrived to the same or best cost. So if minimum costs at next state equals cost, so we either just added it or we're matching the same cost, so we're not improving. We will also make sure that we add it as or hash set is better actually, as a source state for the state. So source states sources will include it. So we include it and then add it to add the state as the source for that minimum cost of that value. And if we change the minimum cost, we also need to make sure that source state at next state is empty. So we have to empty that. And actually, that means that we don't have to check if the value is there, because it's always going to be there. So either we just initialize it with a new value, or we add to it here if we are matching the same value. So if we decrease the best cost, we reset the source state value, and then afterwards we also add the new minimum value there, so we will never lose the state. So finally, when we finish with this, we will backtrack. So we will have to, well, best path tiles. It's going to be a new hash set state. And we will find, so for each direction in directions. So actually we need to know the minimum. So let's go back to what we had before. So now for each direction in directions without diagonals, where minimum costs are your default for basically this whole thing. Well, the final state for the direction equals best end state. So only for the best possible end states we will be backtracking. So yes, so we'll be backtracking. So how do we backtrack from there? So we'll do some kind of, we can do another queue. Backtrack queue. So queue new state and direction. So we'll add those states there, and then we will be looking for the previous states from. So while we'll have something in the queue, we'll get that thing, and we will check how we got there before. So we'll add the current tile there, and then for each of the source states, we will add that back to queue, and we'll continue until we are done completely. We empty the queue, because finally we will return the best path tiles count. So that will be enough, I think. It might not be the most efficient way to do it, but it should work. So let's see. 81, that's a little bit more than I would prefer. All right, so let's see. Oh, all right. I'm adding the state, but I should be adding a point, or no, not here, but point here. So I only need the position, not the state itself. That should be better. Hopefully this, yes, 64. So let's see what happens with the big input. 545. And that is correct. Okay, so we have day 16 finished and done. Tune in for the second video where ChatGPT will also attempt this problem. And I will see you tomorrow, or actually maybe today, for day 17. I will be continuing with my catch up for the remaining missing days. So see you then.